In this video, we're going to take a look at an important definition for vector functions and take a look at our first example. So as we move down here, we'll see that our first definition states, if I have a vector function that's of the following form. Notice again, I have a function r of t. My r is bold because I'm saying that this is a function that's going to output vectors. And you can see that over here from the formula. My formula is actually a vector, and the three components of that vector each are their own formula, which apparently depends on a variable of t. Okay. So this f of t, g of t, and h of t are called the component functions of R. So the way that a function like this would work is you give me a value of t, I can plug it into each of the little f, g, and h formulas, and that will tell me each of the three components that I need for my vector. Okay. So let's take a look here at example number 1. We can see here that we have a nice vector function. Its f of t is this square root function here. Its g of t is the cosine of t. And then its h of t also happens to be a square root function. So what this question is going to ask us to do is something that's very, very basic that we typically do with all functions. We're interested, what is the domain of a given function? Remember that the domain is just what is the set of all possible input values that we can use here. So we can go through here and start to kind of think about this one piece at a time. So I'm going to go ahead and start to write out here that for f of t, which equals the square root of that 4 minus t squared, there's going to be some set of t's that are okay to use and some set of t's that are not okay. Clearly, t's that are not going to be okay would be any t, I guess, that forces a negative to occur underneath the radical, and then I'm going to be entering the world of complex numbers, and I don't want to deal with that here. Okay. So we're going to have to think here, like what's the largest that t could possibly be here, so that I don't end up with any negatives underneath the radical. Well, it seems like here actually 2 would be the largest value for t. And likewise, I think negative 2 would be the smallest possible value that t could be. Anything in between is going to be fine, because then I'm just going to be doing 4 minus something smaller than 4. But I don't want to use a value like 3 or 7, because then I'm going to be subtracting something larger than 4. So I'll say that for this function, the domain is, and so I'll go ahead and write this in some interval notation, but it's negative 2 to 2. Keep in mind here that these are values for t. Okay, those are values for t. Now let's go ahead and continue to do this for each of the individual components of our vector function, and then we'll try to figure out what the domain would be for the entire vector function. Okay, so let's see. For g of t, which is the cosine of t, the domain is, well, here the domain's pretty easy because I know that the cosine graph is nice and continuous, right? There's no holes, gaps, jumps, vertical asymptotes, anything weird like that. So my domain is actually any t value from negative infinity to infinity. There are no off-limit values for this portion of the vector function. Finally, though, I can see that for my h of t, which is that square root of t squared minus 1, I'm going to, again, have to think carefully about what values t can be so that I don't end up with negatives underneath the radical. Now here, actually, the issue is that if t goes too small, for example, if t is 0, then I'm going to have a problem. So what I can see here is that the smallest that t could really go is, I guess, as far as I want, right? Plugging in negative 10 billion is perfectly fine, but I do kind of reach a limit when I get to, say, negative 1. Plugging in negative 1 would be perfectly okay here, because that would just create 0 under the radical. But actually, anything from negative 1 up to 0 is off limits. And in the same way, anything from 0 up to 1 is off limits, but anything after 1 would be perfectly fine. You might recall we use this little U or cup symbol here to represent that we're doing either or of these. You could pull a value of t from either of these two sets. Okay, so all of these intervals here are representing possible values that t can take on. But we were only looking here at one portion of the vector function at a time. So if I wanted to find the domain for the entire vector function, what I would have to do is I would have to kind of think about what t's are allowed in all of the parts. So for example, the value of negative 50 is not allowed in the first part, f of t. It is allowed in the second, and it's not allowed in the third. So negative 50 is not a number I can plug into my given function. So in general, I'm kind of looking for the overlap of all of these values. Ultimately here, we can see that R of t has a domain. And let's see, it looks like I can definitely not use any value smaller than negative 2. But negative 2 would be okay in every one of these every one of those sets or portions, right? Negative 2 isn't a problem in any of the pieces of the vector function. And I can actually go all the way up to negative 1. That's perfectly fine. That works in every single one of these vector functions. However, I can also go from the value of 1 all the way up to the value of 2. And these values work in every single one of the pieces of the vector function. And there are no other values of t that could possibly work in all three of those component functions at the same time. So what we've done here is we found the domain. These are the acceptable values of t to try to input into our vector function. So it's slightly more complicated than just finding the domain of a regular old function that we would have looked at back in an algebra class or Calc 1 or Calc 2, but ultimately it's the same basic idea. We just have to look for that overlap between the different component domains. Okay, in the next video, what we're going to start to do is to take a look at exactly how we can start to imagine what a graph like this might look like. And we'll go ahead and use the 3D plotter to help with that.